Hello students, today we are going to discuss Fraunhofer diffraction. In the earlier classes we discussed about interference diffraction and we also discussed Fresnel diffraction. We did ample amount of discussion on the difference between interference and diffraction. Now Fraunhofer diffraction is kind of a limiting case of the Fresnel diffraction. In the Fresnel diffraction, the sources and screen should be at finite place from the obstacle. But in Fraunhofer diffraction, the source and screen, the distance does not matter here. The thing which matters is angle of inclination. In this case, the source and screen or both can be at infinite distances from the obstacle, means from where the diffraction will happen. From that point the screen can be at infinite distance. Now you will be wondering, if these are at infinite distance, then how the lights are going to superimpose? Now for this we will use the convex lens to make the light converge at a certain point. The diffracted light will converge at the certain point. So in Fraunhofer diffraction, let's discuss first the Fraunhofer diffraction due to a single slit. Now in your notes you will see that there are differences written over there between interference and diffraction. Interference is the superimposition of light waves from two coherent sources, or we can say that superimposition of two or more than two wavefronts. But in diffraction, the superimposition of secondary wavelet sources happen. Now, this was assumed by Fresnel, and he developed a theory by some assumptions, some Fresnel assumptions, right? And we already discussed some cases in which the diffraction happens from like some straight edge or some circular edge. We already discussed these kind of thing, but those diffraction were because of spherical wavefront or circular wavefront. Now if you use a planar wavefront, which is in this case Fraunhofer diffraction, the wavefront should be a planar one, right? Like the Fraunhofer diffraction at a single slit. Now let's consider an experimental setup in which there is a source over there and there is a lens. Now this lens is used to make the spherical wavefront as a planar one, because if you place the source at the focus point of this lens, this convex lens, then the spherical wavefront will be converted into planar one. The light will make the image on infinite distance. Now this wavefront, this planar wavefront falls on this obstacle or this slit AB. The length of the slit is AB. When this planar wavefront falls on this AB slit, some now the wavefront is kind of disturbed here because of this AB slit. There is an obstacle which is disturbing your wavefront, and because of this diffraction happens, because diffraction is also said to be the bending of light by some obstacle, right? So light will bend from this obstacle. Now how light bends from this obstacle and what is the intensity spectra at a certain distance, we will discuss this in this portion. Now some of the light which is, or some of the secondary violet sources which are undiffracted here, will travel further, and we will consider a point P naught, which is at the center point of the screen, or we can say the perpendicular of this from this central point falls on the middle of this slit. So this is the central point, right? So the path traveled by a secondary violet source from this point A or from this point B, the path traveled by both the point is same by the secondary violet source. So when they superimpose over there, these secondary violet source superimpose over there, they will make the maxima, and this is also known as the central maxima. Now some of the secondary wavelet source gets diffracted, and there are many. So to discuss them, now experimentally we got a condition that if the secondary wavelet source from point A is diffracted and which is following the path, some path, and falling at point P1. Now let's consider another point P at a certain distance from P0. The distance is x. So if secondary wavelet source is traveling from A and diffracted as well by some angle theta from the initial direction of the propagation. Now if this secondary wavelet source is diffracted by some means and then we make it to fall on this point P, and there is another secondary wavelet source traveling from B which also got this diffracted by some angle theta, and we also make that secondary wavelet source to fall upon P1 point. Okay, when they superimpose, the condition is something like this, that the path difference between these secondary wavelet source satisfies the minima condition. Whenever path difference happens to be delta happens to be n lambda, then we get the minima condition here. Whenever path difference happens to be n lambda, we get a minima condition. So to explain this, because for minima there must be some kind of destructive interference or destructive superimposition between these secondary wavelet sources. So to explain this, we consider that the wavefront, the whole planar wavefront falling here at this slit AB, right? This point is A, this point is B. The whole planar wavefront which is falling at this slit AB. Let the opening of the slit is A. The opening of the slit is A, right? So the path difference, and when they travel further and they get diffracted and we make them superimpose at a certain point, then the path difference between the secondary wavelet source starting from A and the secondary wavelet source starting from B is equal to this much, and this is A sin theta. So the path difference is delta is A sin theta, right? And whenever this path difference satisfies the condition of n lambda, we get a minima over there. Now this point P is a secondary minima, and whenever this path difference is equal to odd number of 2n minus 1 lambda by 2, now this condition satisfies the secondary maxima, those points where we get maxima conditions along with the central maxima. Another points wherever we get the maxima condition, those maxima are known as secondary maxima. Okay, beside this central maxima there are another maximas, and these maximas are known as secondary maximas. Okay, and why do we get these secondary maximas? Because the path difference between two secondary wavelet source satisfies this condition, and at those points we get secondary maxima. Now how this can be happen? Now this is a reverse condition kind of interference, because in interference the superimposition of wavefront happens, and we get that the path, whenever the path difference is equal to n lambda, we get maxima points, and whenever the path difference is equal to 2n minus 1 lambda by 2, there happens to be a minima point for interference, right? But in Fraunhofer diffraction happening from a single slit, experimentally we get these two things, right? So how do we explain this? So to explain this, let's consider a planar wavefront falling on this slit having width A. Now we will divide this complete planar wavefront in